Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the second part of Chapter 12 Electromagnetic Oscillations. At the end of this video, the student will be able to analyze the free and damped electromagnetic oscillations in the LC series circuit. Let's remember first charge oscillations between the coil and the capacitor and consequently current oscillations. These oscillations are called free electromagnetic oscillations. The electromagnetic energy stored in a circuit LC in the absence of resistance is W electromagnetic equal W electric plus W magnetic equal half Q squared over C plus half Li squared, equal to half Q maximum squared over C or half Li maximum squared, and it will be constant. The electromagnetic energy stored in RLC circuit with resistance is W electromagnetic equal half Q squared over C plus half Li squared. Of course, it is not constant. Let's focus first at the relation between I and dQ by dt in a capacitor. When the positive sense enters the armature carrying the charge Q, then I equal plus dQ over dt. While when the positive sense leaves the armature carrying the charge Q, then I will be equal to minus dQ by dt. As we see in the first video, the shape of the voltage across UC during the electromagnetic oscillation have a sinusoidal form. Now, in order to prove this analytically, we will determine the differential equation and its solution. This differential equation can be obtained using two methods. The first one by deriving the expression of electromagnetic energy. The electromagnetic energy is equal to magnetic energy plus electric energy, and in the absence of resistance it is constant. So half Li squared plus half Cu squared equal to the electromagnetic energy. Since electromagnetic energy is constant, the derivative of this energy will be 0. So Li I prime plus C UC prime equals 0, and as we know I equal plus dQ by dt and Q equals C UAB, which is equal to C UC. So I will be equal to C UC prime and I prime will be equal to C UC W prime. Replacing these in the differential equation, we will have LC UC prime C UC W prime plus C UC prime equals 0. And since UC prime different from 0, so we will have LC UC W prime plus UC equal to 0. Divide by LC, we will have UC W prime plus 1 over LC UC equals 0. This is the differential equation that governs the variation of UC. Second method, by applying the law of addition of voltages. UAB will be equal to UAD plus UDB. Okay, UAD is 0 since the wire has no resistance, and UDB is equal to minus U coil since it is opposite to the positive sense, so it will be equal to minus L di over dt since the coil has no resistance. So I equal plus dQ by dt and Q equals C UAB equals C UC, then I equals C UC prime and di by dt will be equal to C UC W prime. So UC equal minus LC UC W prime. UC plus LC UC W prime equals 0. Dividing by LC, we will have UC W prime plus 1 over LC UC equals 0. This is again the same differential equation obtained using the method of conservation of electromagnetic energy. Since this differential equation has the form of UCW prime plus omega 0 square UC equals 0, we can say that omega 0 equal 1 over radical LC, and since T0 equal 2 pi over omega 0, so T0 will be equal to pi radical LC, and F0 will be equal to 1 over 2 pi radical LC. F0 is the proper frequency of the LC circuit. Now, this differential equation have a general solution of the form UC equal U maximum sine omega 0 t plus phi. So the shape of UC will be sinusoidal. Since Q equals C UC, so it will be equal to C U maximum sine omega 0 t plus phi, and also Q will have a sinusoidal form. And since I equal dq by dt or C duc by dt, so I will be equal to omega 0 C U maximum cosine omega 0 t plus phi. Now let's study the graphs of energy versus time. As we know, UC equal U maximum sine omega 0 t plus phi have a sinusoidal form. The electromagnetic energy in the case of absence of resistance is constant, so it will be a horizontal line having a constant value. The electric energy is equal to half C UC squared equal half C into U maximum sine omega 0 t plus phi squared. This expression always is positive, and we must note that WC maximum is equal to half C U maximum squared, and at t equals 0 UC equal U maximum. So the graph of UC will have a sinusoidal form. Now the magnetic energy is equal to half Li squared, since I equal C UC prime, so I equal omega 0 C U maximum cosine omega 0 t plus phi, so W magnetic will be equal to half L into omega 0 C U maximum cosine omega 0 t plus phi squared, which is also a positive value. So W maximum magnetic equal half L omega 0 C U maximum squared, and at t equals 0 I equals 0, and so the magnetic energy. So the curve of magnetic energy will have a sinusoidal form starting from 0. Now, we must note that the period of energy is equal to the half of the period of the oscillation. Let's solve now application 2. In the opposite circuit, a capacitor of capacitance C equal 2 microfarad initially charged is connected with a purely inductive coil. The electric energy WC and the magnetic energy WL of the circuit are represented in the opposite graph. At t equals 0, UC equal 2 volt and I equals 0 ampere. Part 1. Determine the differential equation verifying the charge Q of the capacitor during the electromagnetic oscillation in the circuit. First, using law of addition of voltage, UAB equal UAD plus UDB, so equal to 0 plus L di by dt. And since the positive sense is leaving the plate having charge Q, so I equal minus dq by dt, and di by dt equal minus q double prime, and UAB, which is equal to UC equal Q over C, so Q over C will be equal to minus L Q double prime, and Q over C plus L Q double prime equals 0. Dividing by L, we will have Q double prime plus 1 over LCQ equals 0. Part 2, let Q equal A cosine 5 pi t plus 5 be the solution of the differential equation where A is positive. Determine the values of constants A and phi. Since Q equal A cosine 5 pi t plus phi, at t equals 0, Q0 equal A cosine phi. So CU0 equal A cosine phi, replacing C equal 2 millifarad. So 2 times 10 power minus 3 times 2, which is equal to U0. We will have 4 times 10 power minus 3 equal A cosine phi. Now, I equal minus dq by dt equal to 5 pi a sine 5 pi t plus phi. At t equals 0, I0 is equal to 5 pi a sine phi and I0 equal 0. So sine phi equals 0. So we have phi equals 0 or pi radian. But since a is positive, so cosine phi is positive, so phi equals 0 radian. Now, when phi equals 0 radian, we will have a equal 4 times 10 to the power minus 3 coulomb. Part 3. Determine the value of the maximum magnetic energy W, L maximum, stored in the coil. In the free undamped electromagnetic oscillation, we will have W magnetic maximum equal to W electric maximum, so it will be equal to half C U maximum squared across the capacitor. At t equals 0, UC equal 2 volt, so WC at t equals 0 equal WC maximum equal half C UC 0 squared, and it will be equal to 4 times 10 to the power minus 3 joule. Part 4. Determine the value of the inductance L of the coil. Since the period of the oscillation is equal to twice the period of the energy, so T0 equals 0.4 millisecond. And as we know T0 equal 2 pi radical LC, replacing the values we will have L equal T0 squared over 4 pi squared C, which is equal to 2 times 10 to the power minus 6 Henry. Now, as a summary, during the undamped free electromagnetic oscillations in a circuit LC, the differential equation that governs the variation of UC is UC double plus 1 over LC UC equals 0. The general solution of the differential equation UC double plus 1 over LC UC equals 0 is UC equal U maximum sine omega 0 t plus phi, and the proper frequency of the LC circuit is F0 equal 1 over T0 equal 1 over 2 pi radical LC. During the undamped free electromagnetic oscillations in a circuit LC, the period T energy of the oscillations of energy is half to the proper period T0, so T energy equal to 0 over 2. This is the end of part 2. Thank you for your listening.